Okay, we're going to talk about how matrices relate to systems of equations, systems of linear equations. We're going to start with a simple example. 3x plus y is 7, and 5x minus 2y is 19. Usually this is taught in, not with matrices, but with other methods of solving in a freshman algebra class. You'd probably learn how to graph these two systems of equations, these two equations. You'd look to see where the line intersected, and maybe you could tell what the answer is just by looking at the graph. Or you maybe did something called substitution or linear combination, sometimes called elimination. So there's a couple different methods that you might have learned as a freshman, or maybe even earlier if you took an early algebra course. So there are ways to solve these without using matrices, but we're here today to tie in the matrices to solving systems of linear equations, and here's how we're going to do it. The first thing we're going to do is create a matrix of just these coefficients of x and y. I'm going to make a little 2 by 2 matrix, fairly simple. 3, 1, 5, and negative 2. Okay. Then we're going to create the variable matrix, and it's just going to look like this. We got an x and a y. Finally, we're going to say that equals the resultants, or some people call it the answer matrix, right? What is the answer to the question we're asking? Okay, what is 3x plus y? Well, it's 7. Okay, if you'll think back to your matrix multiplication, we can multiply this matrix by this because it's a 2 by 1, or 2 by 2, and this is a 2 by 1. So the number of rows here matches, or the number of columns here matches the number of rows here. So it's certainly possible to multiply. And look what you would get. If I multiply this row by this column, I'll have 3x plus y, and that should get me a 7, which is exactly what this is saying up here. Then if I do 5x minus 2y, 5x minus 2y, I should get 19, which is exactly what this is saying. So this set of matrices being multiplied gives me exactly the same idea. It's basically saying the same thing. If I can find x and y, I can solve this system. Okay, we're going to use a principle that you should be already familiar with. If I'm multiplying a number, let's say 7 times some number a, and it ends up being 21. There's basic problem solving skills. You'd simply divide both sides by 7, or another way to think of it is multiplying by the inverse of 7, right? Multiplying by the inverse of a number is just like dividing. So if we multiply both sides by the inverse, we can find out that a is really just the number 3. And that's exactly what we're going to do here. I'm multiplying this times this and getting this. So if I take the inverse of this and multiply it, this becomes the identity matrix, and the identity matrix times this is just this. So multiplying this times a 2 by 2 is going to give me a 2 by 1, and will tell me exactly what x and I should be. So let's go ahead and use this principle. We're basically just going to multiply by the inverse of the matrix, but the first trick is let's find the inverse of this matrix here. And if you remember, when we're finding the inverse, the first thing we have to do is calculate the determinant. If the determinant is 0, then we can just stop because there is no solution. If it's not 0, then we can just keep on moving on. So let's do 3 times negative 2 is negative 6. 5 times 1 is 5. Negative 6 minus the 5 is negative 11. So now we have negative 1 over 11. I could have put the negative down here, but just better to write it with the numerator. I'm going to multiply that times the matrix I get when I move this main diagonal, swap the main diagonal, make the other diagonal negative. So that's easy enough to do. The negative 2 comes up here. The 3 goes down here. 5 is positive, so it becomes negative. 1 is positive, so it becomes negative. And now I just simply multiply each one of these things by negative 1 over 11. And we end up with a positive 2 elevenths, positive 1 11th, positive 5/11, and finally negative 3/11. Now, it looks like we got a lot of fractions there, and we do, but don't worry about that. Fractions are just numbers, and that we can just go on. I mean, there's plenty of ways of doing this math. So let's go ahead and take our inverse matrix and multiply it times this matrix. So I'm going to rewrite it: 2/11, 1/11, 5/11, negative 3/11. This is our inverse of this matrix up here. And I'm going to multiply it by the 719. And what I should get when I'm done is a 2 by 1 matrix, 2 rows, 1 column, and the two numbers are going to represent the x and y, because essentially I'm dividing out both sides. Multiplying by the inverse is like dividing. So let's have a go at it. In order to get the first number of this multiplication, I'm going to take these two numbers and multiply, these two numbers and multiply, and then simply add them together. So here I got 7 times 2/11 is 14/11, and here I'm going to have 19/11, which I'm going to add together, and that actually gets me 33/11. 33/11 is just 3. So I've already found one of the two solutions, or found the x solution anyway. Now let's go ahead and take this row times this column. 5/11 times 7 is 35/11. Then I'm going to subtract 3 times 19. It would be negative 57/11. So I'm going to subtract 57/11, and that gets me negative 22/11, which is just negative 2. So now I know that my x is 3 and my y is negative 2. And that's how you go about solving a system of linear equations with matrices. And you might be thinking it was a lot easier when we used those other methods of substitution and linear combination, and I would say absolutely true. When it comes to 2 by 2 matrices and systems, this may not be your method of choice because it does take a little more work. We simply multiplied the top row by 2 and did a linear combination. We probably could have solved this much quicker. But what I want you to kind of keep in mind is when this grows to, say, a 3 by 3 matrix or a 4 by 4 matrix, computationally, the matrix methods start getting better and better all the time, and they scale much better. Also, if you're writing a computer program to do this, using the matrix method is much more straightforward. There's few decisions, there's no decisions that have to be made. You simply do the calculations, and it's much friendlier to computational algorithms. So there, for a couple reasons, we like to understand how to do this with matrices. And that should tie in how matrices relate to systems, and in fact how you can even solve one using an inverse matrix.